Welcome back to the Deep Dive. Today we are tackling what might be the single most hyped technology in the entire automotive world.
Oh, this is a big one.
It is. If you follow EV news, even, casually, or if you just own a smartphone that dies by 4 p.m., you have seen the headlines. I'm talking about the holy grail of energy storage.
Hmm.
We're talking about batteries that promise a 1,000-kilometer range, charging from 0 to 80% in literal minutes, and this is the crucial part zero risk of catching fire. We're talking, of course, about solid-state batteries.
Is a technology that is always just around the corner, isn't it? It feels a
Yeah.
little bit like the nuclear fusion of the car world, always 5 years away.
Exactly. I feel like I've been reading about this for a decade. Toyota promised them by 2025. Samsung said they were right there, and yet I walked out to my car this morning, and guess what?
Still lithium ion?
Still running on a lithium-ion battery, the exact same tech in my laptop and my phone. So the question we really need to answer today is,
Mm.
what is actually going on? Is this vaporware, or is it actually happening?
It is happening, but perhaps not in the way the marketing brochures would have you believe. It's a lot messier and, frankly, a lot more interesting from an engineering perspective than just better batteries.
So our mission today is simple. We are going to cut through all that noise. No marketing fluff, just the engineering reality. We're going to look at the chemistry, the costs, and the absolute production hell that stands between us and that 1,000-kilometer drive.
Sounds good.
But before we get into the nitty-gritty, I need to take a second here and do something important.
What's that?
I just want to say a massive thank you to our listeners, to the learners. Seriously, we see your emails, we see you sharing the show, and whether you're an engineer prepping for a meeting or just someone who's, insanely curious about how the world works, we really appreciate you tuning in.
We do.
We know this topic is confusing. There's so much conflicting info out there, so this deep dive is dedicated to clearing that up for you. So seriously, thank you for being here and trusting us with your time.
Absolutely. Critical thinking is in short supply these days, and we appreciate you diving deep with us. And to help us do that today, we have a serious stack of sources.
Let's hear it.
We're pulling from technology roadmaps by the Fraunhofer Institute, market analysis from TrendForce and Bloomberg NEF, and some very, very candid industry reports coming out of China and the US.
Okay, let's unpack this. First things first, clarity. We need a baseline. What exactly is a solid-state battery? Because I think a lot of people just assume it's a better battery, but physically, what is different inside the casing?
It really all comes down to one component,
Right.
the electrolyte. Let's visualize the battery you have now, a standard lithium-ion battery. You've got a cathode and an anode.
Right, the positive and negative ends.
Exactly. And between them, occupying that space, you have a liquid electrolyte.
Okay.
Think of that liquid as a highway for ions to travel back and forth. When you charge, the ions move one way. When you drive your car or use your phone, they move the other way. That liquid is what makes the movement possible.
Right. And the issue with the current tech is that the liquid itself is problematic.
It's volatile. It's a chemical solvent. It's flammable. And it has speed limits. The ions can only move through that liquid soup so fast without generating too much heat.
So a solid-state battery simply,
Yeah.
it just deletes the liquid.
Effectively, yes.
Yeah.
It replaces that liquid highway with a solid material. It could be a ceramic, a type of glass, or even a polymer. But the key functional difference is that there is no sloshing liquid inside that cell. The highway becomes a solid bridge.
Simple enough concept. But why is everyone so obsessed with this? Why are companies spending billions of dollars to reinvent the wheel here? If liquid works, why change it?
It comes down to three main reasons.
Right.
Let's call them the three promises. First, and this is paramount for manufacturers, is safety.
Right.
As I just said, liquid electrolytes are flammable and toxic. If you puncture a standard battery in a bad crash, you can get a thermal runaway event, a fire.
Which is the headline nightmare for any EV company. You see one car fire on the news and
It dominates the cycle for weeks.
Exactly. Solids generally don't catch fire. They are chemically and thermally stable. You can puncture them, and typically they just sit there. That safety profile changes everything. It means you need less cooling equipment, less heavy armor around the battery pack.
Which leads right to the second promise, doesn't it? If you don't need all that armor and cooling plumbing.
You get better energy density. This is the big number everyone chases. Our sources indicate that while current batteries hold about, say, 150 to 300 watt-hours per kilogram, Solid-state batteries could theoretically hit 300 to 900.
Let's contextualize that for everyone. That means you could have a car that goes twice as far on a battery of the same weight.
Or,
Or, conversely, a car with the same range that weighs half as much.
precisely, it breaks a weight spiral that a lot of EVs are currently stuck in. We keep making cars heavier to get more range, which of course makes them less efficient. Solid-state could break that loop. And the third promise is the one consumers care about most: charging speed.
The gas station experience. I want to plug in, buy a snack, and leave. And because of how the ions move through these solid structures, and because the materials can handle much higher heat without degrading, we're looking at potential charging times of 10 to 80% in just 3 to 15 minutes.
That's the dream. Fill up in the time it takes to grab a coffee. But, and here's the big pivot, if the tech is so good and the concept is so simple, swap liquid for solid, why aren't we driving them? This brings us to what one of our sources called the crisis of credibility.
Ah, yes. This is where it gets really fascinating. The term solid state has become a massive marketing buzzword, and frankly, it's starting to lose its meaning.
There was a great analogy in one of the sources we looked at.
The gelato one.
The gelato versus frozen dessert analogy. I loved this. It's the perfect way to visualize the marketing trick. So you go to the store, you buy what you think is ice cream, but the label says frozen dairy dessert.
Right, because it doesn't meet the legal definition of ice cream. It's got too much air or oil in it or something.
Exactly. And in the battery world, we have all solid-state batteries which have zero liquid. That's the pure gelato. But then we have companies announcing these solid-state breakthroughs that are actually
Semi-solid or quasi-solid.
so they're just blurring the lines.
Significantly. A semi-solid battery might still contain about, say, 10% liquid electrolyte. It's just enough to help the ions jump across the interface between the solid parts. A quasi-solid might have less than 5%. They're basically wetting the solid material just a little bit to make it work.
Okay, but let me play devil's advocate here. Does that really matter? If I'm a driver, do I care if my battery is 5% liquid if it charges in 10 minutes and doesn't explode?
And that is the pragmatic argument, right? If the user experience delivers the range and the safety, the specific definition matters less to the consumer. In fact, we are already seeing these semi-solid batteries on the road.
Oh, really?
Yeah. NIO and MG are deploying cars with these hybrid batteries right now. They're the bridge technology. They give you some of the benefits of solid state without the manufacturing nightmare of going 100% solid.
So the pure solid state, the stuff with zero liquid, that's the hard part. Let's get into the chemistry here, because I was surprised to learn there isn't just one type of solid state battery. I thought it was just solid state, but it's actually more like a cage match between 3 different materials.
Correct. It is not a monolith. According to the Fraunhofer Institute roadmap, there are 3 main contenders fighting for dominance: polymers, oxides, and sulfides. And here's the kicker. Each one has a sort of fatal flaw they are trying to fix.
Okay, let's break them down. Contender number 1, polymers.
Polymers are the most mature technology. They're basically plastics. We actually already have these in some electric buses, like the Blue Bus fleet in Europe. They're relatively easy to manufacture because they're flexible. You can roll them up like a carpet.
There's always a but.
But they have terrible conductivity at room temperature. The ions really struggle to move through the plastic unless it's hot. They need to be heated to about 50 to 80 degrees Celsius to work efficiently.
So not great for a passenger car sitting in a driveway in Minnesota in January. You'd spend all your battery energy just trying to warm up the battery so it could start the car.
Exactly. Great for a bus that runs all day on a schedule, but terrible for a family car that needs to start instantly for a quick trip to the grocery store.
Okay, contender number 2, oxides, or ceramics.
These are very chemically stable and tough. They're safe. The problem is purely physical. They are brittle. Think of a ceramic dinner plate. It's hard, but if you twist it or stress it, it cracks.
And a car is basically a vibrating box moving at 70 miles per hour over potholes.
Right. If the electrolyte cracks, the battery fails. Plus, making them is incredibly hard. You have to sinter them. Sintering is basically baking the ceramic at extremely high temperatures. We're talking over 1,000 degrees Celsius to fuse all the particles together.
That sounds incredibly energy intensive.
It is. It takes a massive amount of energy, which drives up the manufacturing cost and the carbon footprint, ironically. So you have a battery that is hard to make and easy to break.
Not a winning combination yet. Okay, so polymers are too cold, oxides are too brittle. What about contender number 3, sulfides? The sources seem most excited about these.
Sulfides are the speedsters. They have the best conductivity by far. The ions move through them incredibly fast, sometimes even faster than in liquid. This makes them the best candidate for that super fast charging we talked about. Toyota is betting big on these.
Let me guess. There's a catch.
A big, smelly catch. Sulfides are incredibly sensitive to moisture. If a sulfide electrolyte touches even a tiny bit of humidity in the air, it reacts and releases hydrogen sulfide gas.
Which is
Highly toxic and smells like rotten eggs.
not exactly a selling point for a luxury vehicle. New car scent, now with a hint of lethal rotten egg.
And practically, it means you can't just build these in a normal factory. You have to manufacture them in extremely controlled dry rooms or inert gas chambers. This drives up the cost and the complexity enormously. You can't have a single leak in the production line, or you have a major safety hazard.
This brings us perfectly to the next section of our dive. Production hell. We know the science works in a lab. We can make a coin-sized battery work perfectly. But scaling it up to millions of cars seems to be the real nightmare.
It is. Let's talk about cost, because that is the ultimate decider. Right now, a standard lithium-ion battery costs the manufacturer about $115 per kilowatt hour.
Okay, so a 100 kilowatt hour pack, which is a big battery for a long-range car, is roughly, what, $11,500?
Roughly. Now, estimates for solid-state batteries currently sit somewhere between $400 and $800 per kilowatt hour.
Whoa, so we're talking 5 to 10 times the cost.
Yes. So that same battery pack, instead of costing 11 grand, could cost $80,000 just for the battery.
That makes the car completely unaffordable for mass adoption. You can't put an $80,000 battery in a $30,000 car.
You can't. And it's so expensive because of the manufacturing process. You can't just take a factory making liquid batteries and switch a lever. You need entirely new equipment. For oxides, you need those massive high-temperature furnaces. For sulfides, you need those hermetically sealed dry rooms. And then there's the pressure issue.
Pressure.
This is a detail often left out of the headlines. To keep the solid layers touching each other so the ions can move, especially with the lithium metal anodes they want to use, you often need to apply immense pressure to the cell, sometimes over 10 megapascals.
10 megapascals. Put that in perspective for us.
It's like stacking a gym weight on every single square inch of the battery surface. You can't just tape the battery together. You need heavy, expensive steel casing and clamping mechanisms to maintain that pressure for the life of the car.
Which adds weight back into the car, defeating some of the purpose.
Exactly. And there's one more ghost in the machine. Dendrites.
I read about these. I thought solid batteries were supposed to fix the dendrite problem.
That was the hope. Dendrites are these little needle-like spikes of lithium that grow inside the battery when you charge it fast. In a liquid battery, they pierce the separator and cause a short circuit.
Boom.
Boom. In a solid, it turns out lithium is tricky. Even in solids, these dendrites can find tiny cracks or grain boundaries in the ceramic and just push right through. They can crack the electrolyte. Think of it like tree roots breaking up a concrete sidewalk.
So even the indestructible battery has an Achilles heel.
It does. Scientists are working on coatings and things to stop this, but it's another major hurdle.
That is disheartening. But there's another thing the experts mention, the moving target challenge. It's not like standard batteries are just sitting around waiting to be replaced.
This is a crucial point that I think investors often miss. While solid state is struggling to figure out how to manufacture at scale, standard lithium-ion and LFP, that's lithium iron phosphate batteries, are getting better every single year.
Right. LFP batteries are already in tons of cars. They're cheap, they're durable.
And they're evolving. We're seeing LFP mixed with manganese to hold more energy. We're seeing silicon anodes being added to liquid batteries to speed up charging.
So solid state isn't competing with the battery of today. It's competing with the liquid battery of 2030, which will be much cheaper and much better than what we have now.
Exactly. Solid state has to chase a benchmark that keeps moving further and further away. By the time solid state is ready, liquid batteries might already offer 800 kilometers of range and fast charging for a fraction of the price.
So let's get real. I'm a listener. I'm looking to buy an EV in the next few years. When can I actually buy a car with a true all-solid-state battery?
Okay, if we synthesize all the roadmaps from Toyota, Samsung, Nissan, and the market analysts, here is the realistic timeline.
Lay it on me.
Phase 1 is basically now 2024 to 2027. This is the pilot phase. You will see headlines about Toyota or Nissan launching a vehicle, but be warned. These will be small demonstration fleets.
Like a few hundred cars.
Maybe 1,000 cars total. Not something you can walk into a dealership and buy. It's a proof of concept.
Okay, so mostly PR moves and real-world testing. Phase 2.
2027 to 2030. This is what we're calling the premium phase. You might see these batteries in a high-end Lexus or a luxury Mercedes. We are talking about $100,000 plus vehicles where the buyer can absorb that massive cost difference we talked about earlier.
So for the average person,
You are looking at phase 3, 2030 to 2035 and beyond. That is when mass market commercialization might begin, and I have to emphasize might.
2035, that feels like a lifetime away in tech years.
And here is the really sobering statistic from our sources at TrendForce. Even by 2030, solid-state batteries are expected to hold less than 1% of the total EV battery market.
1%.
Less than 1%. Even by 2035, it might only be slightly above 1%.
Wow. That really puts the hype in perspective. We talk about it like it's taking over tomorrow, but in reality, liquid batteries, lithium-ion, are going to be king for a long, long time.
Absolutely. Liquid is king. It has the supply chain, the economies of scale, and the proven reliability. Solid state is the future, but it is a distant future.
So what does this all mean for us right now? Should we be disappointed?
No, I don't think so. I think it means we need to view this technology as an evolution, not a revolution. We aren't going to wake up one Tuesday and suddenly every car has a solid-state battery. We are going to see a transition. We'll see those hybrid semi-solid batteries first.
Right.
They offer, say, 80% of the benefits without that manufacturing nightmare.
That actually makes a lot of sense. Why let perfect be the enemy of the good? If a semi-solid battery gets me 800 kilometers and charges in 12 minutes, I'm probably happy. I don't really care if there's a teaspoon of liquid inside.
Precisely. And that raises the final big question for the industry that the sources all kind of hint at.
Which is?
If these bridge technologies, the semi-solids, advance quickly enough, and if standard LFP batteries get good enough, will we even need full, expensive solid-state batteries for the average family car?
That is an interesting thought. Maybe the Holy Grail ends up being a niche product for supercars and performance vehicles, while the rest of us drive on good enough tech that costs a fraction of the price.
It is a very real possibility. The market usually chooses the most cost-effective solution, not necessarily the scientifically perfect one. It's like VHS versus Betamax, right? Betamax was better, but VHS was cheaper and good enough.
Great comparison. Well, there you have it. Solid-state batteries. Incredible science, massive potential, but stuck in a very expensive production hell for the foreseeable future.
But definitely worth watching. The breakthroughs are happening, just slowly.
Always worth watching. I want to thank you all again for listening to the deep dive. We hope this cleared up some of the confusion between the headlines and the reality.
And don't forget to check back in with us in 2030 to see if we were right.
We'll set a calendar invite. Thanks, everyone. Stay curious.